Welcome to the Crazy Hat Chemist. So today we're doing another video on gases number 4. Bam! So today we're talking about Graham's law of effusion, Graham's law of diffusion. Same thing. Okay, the rates of effusion or diffusion of two gases at the same temperature and pressure are inversely proportional to the square roots of either their densities or their molar masses. Okay, so effusion is the movement of gas molecules through a small opening. So take a balloon example. It looks like it's relatively solid and it will hold in all that gas. However, there are actually small openings in that rubber balloon. Okay, and then so that's the definition of effusion. Movement of small molecules, or gas molecules rather, through a small opening. If you were to take one room and have it adjacent to another room and have the rooms closed off from one another, then drill a hole in one room, then the gas molecules will effuse out of or into the hole that you drilled through. Okay? Don't try that at home. All right. Diffusion is the movement of gas molecules from one area to the other, but not going through a small opening. An example of that is if someone were to spray perfume in the room. Or if in your class or something like that and someone opens up a banana and starts eating a banana, then the people next to that person eating the banana will smell it first. And the last people to smell that banana will be the furthest away from them. So the gas molecules are diffusing throughout that room, but not going through a small opening. Okay? All right. So this is Graham's law. We can calculate how much faster one gas is compared to another gas using this mathematical equation here. That is, the rate of gas A over the rate of gas B is equal to the square root of an inverse relationship of either their molar masses or their densities. All right. So which gas will effuse out of the holes of a balloon faster, helium or oxygen? So this is one of the things I want you to do one of these days. Go to a party store and get a balloon that's a rubber balloon like you see in this picture and fill it up with helium. Tie it in a knot, take it home. And also I want you to get one of those Mylar balloons. Okay, fill it up with helium, tie it in a knot, bring it home. Place both of those balloons, cut off the little ribbons there and let them float to the ceiling in your room. And then just watch them over days and then think about what is actually happening. Why are you paying extra money for the Mylar balloon as opposed to the less expensive rubber balloon? Okay, you should see that over time the rubber balloon is going to start to decrease in size, shrink, and therefore it will also fall. Okay, whereas the Mylar balloon will be staying on your ceiling for days and days and days, if not for weeks. And what is the difference between the rubber balloon and the Mylar balloon? The rubber balloon has small openings that are larger openings than the Mylar balloon. The Mylar balloon has exceedingly small openings. And therefore, it's very difficult for the helium to escape through these small openings and effuse. Whereas the rubber balloon, there are actually small holes in the rubber balloon and the helium molecules will effuse out of it. That's why the balloon shrinks. That's why the balloon sinks in the air, eventually down to the floor. Okay, think about that. Okay, and then we can do some mathematical operations here. So one of the things you need to do is you need to get the formula for helium and the formula for molecular oxygen. So what is the formula for helium? That's just He. What is the formula for molecular oxygen? That is O2 because it's one of the diatomics. Okay, and so we've got helium and oxygen in our balloon here, and which one is going to effuse out of the holes of this balloon faster? And then how much faster? Okay, so you should be able to figure out that helium is lower in molar mass than oxygen. So helium will effuse faster than the oxygen out of that balloon. No matter what kind of balloon it is, it doesn't matter. The oxygen will move slower out of that balloon. Okay, one reason is the helium is smaller and it will effuse out of the smaller holes of that balloon. The oxygen is larger and it has a harder time getting out of the balloon holes, if you will. Okay. Furthermore, the helium is moving much faster at the same temperature because its mass is less and therefore the kinetic energy is the same because they're at the same temperature. So that the helium molecules inside the balloon are bouncing against the sides of the balloon at a much faster speed, at higher velocity than that of the oxygen. And they're smaller, that's why they're moving faster. Okay? An analogy of this is if you were to put someone on a skateboard and push them with a certain amount of energy, and then take your car, put it in neutral, and push that with the same amount of energy that you push someone with a skateboard. Who is going to move faster, the person on the skateboard or the car in neutral? Well, of course, the person on the skateboard. Why? Because it's lower in mass compared to that of the car. Okay, so at the same temperature, at the same kinetic energy, okay, the less massive object is going to be moving faster than the heavier object. All right, so let's plug this in. Helium and oxygen are in the same balloon. Which one moves faster and by how much? Well, I've already answered the question, which one moves faster, because we know the molar mass for helium is less than that of oxygen. So we can answer that question right now. Which one is faster? Helium. Which one is slower? Oxygen. Now we're going to use Graham's law to figure out how much faster helium is or how much slower oxygen is. So we're going to be using Graham's law. That's right down here in the lower right hand corner, and I've plugged in some numbers. I've used my periodic table to acquire the molar mass for oxygen and for helium. Of course, we already know that helium is monoatomic and oxygen is diatomic. Okay, I'm going to do the division here. My units of grams and moles both cancel out, and I just have a ratio without any units here. And that means that this is the rate of helium is 2.83 times faster than that of oxygen when they are at the same temperature and pressure. Okay, if I had the speed at which the helium was moving, then I could determine the speed at which the oxygen is moving, or vice versa under that case. All right, now let's answer another one. Which gas is slower and by how much? We already answered the question of which gas is slower, and that's oxygen. Now, by how much? We're still using Graham's law, but since we've already used Graham's law to figure out which gas is faster and by how much, I'm going to use that information and then work around this example here mathematically. So you should understand that the reciprocal of the top answer is going to be the answer to the second one. And that is the rate of oxygen over the rate of helium, and that will be 0.354. So this is 0.354 times slower, because I want you to look at the numbers 2.83 and 0.354. The 2.83 is greater than 1. When you get a number greater than 1, that means that that gas, in this case helium, is faster. If you get a number 0.354, that is a number that is less than 1, then you know that that gas is slower. It's really simple. If you want to get which one is slower or faster, just take the reciprocal of either one that you had previously. Okay, that is another crazy hat video, and I got a crazy hat here. I got a cat hat. My cat is just taking a nap over there, and so this is a cat hat for the Halloween time. If you like that video, give me a thumbs up, subscribe to my YouTube channel, and I'm going to see you next time for more gaseous problems.